Let's start. And today we are happy to have Zhiwei Yun from MIT. He will speak about the regular Deligne-Simpson problem. So please.
Thank you, Professor Sobelman, for the invitation. It's my pleasure to give a talk here. So I'm gonna report on my joint work with Konstantin Jakob on irregular Deligne-Simpson problem. So I first give a very general introduction to what Deligne-Simpson problem is. Then I will report some facts about irregular connections and leading to the statement of our result. Okay. So the Deligne-Simpson problem is a problem about existence of connections. Existence of connections or local systems with prescribed local monodromy. So for example, on a Riemann sphere, if we puncture several points and we want to find let's say rank n local system on the Riemann sphere with several points removed. So rank R local system with n points removed. So this, we all know that the datum of a local system is a representation of the fundamental group. So pi1 of this open Riemann surface, we want to find an R-dimensional representation. We want to find such a thing with a prescribed local monodromy. So that means around each puncture, we are given a conjugacy class of matrices Ci inside GLR. So this will be the prescribed monodromy. When you go around the puncture, so for example, you think of it as a solution to some ordinary differential equation, and go around a puncture, your solution will undergo monodromy matrix, and that the conjugacy class of that matrix is given to you. And the problem is to decide whether you can find such a local system with all the Ci's given. Okay, so of course we can reformulate this into a purely algebraic question about matrices, because we know that the fundamental group of P1 minus several points is a free group on n, so n minus 1 generators. So if I have n punctures, then it's a free group on n minus 1 generators, right? Or in other words, so this is a, if I call this gamma I and gamma 1, gamma n, subject to one equation, gamma 1, the product is 1. So to give such a homomorphism to GLR is the same thing. So the above problem is equivalent to finding matrices AI within the given conjugacy class such that the product is 1, is the identity matrix. Okay, so this AI will be the image of gamma I under this representation. So formulated this way, it's just solving matrix equation. But the existence or non-existence of solution can be not completely obvious. For example, let me give an example where the solution doesn't exist, but not in a completely obvious way. So let's take r equals 3, and let's take CI. Each CI, so maybe let's puncture 3 points, 3 punctures. So I will give 3 conjugacy classes. Let's say the first one, it looks like diagonalizable with eigenvalues 1, 1, A. C2 is diagonalizable with eigenvalue 1, 1, B. C3 is again diagonalizable with some other eigenvalues where C and a D and E are all different from 1. Then if you try to find 3 matrices from these 3 conjugacy classes, you can never make the product equal to 1. And so no solution to A1, A2, A3 equals identity. The reason is very simple, because if if I have already chosen A1 and A2 from these 2 conjugacy classes, then they will each have a fixed point plane, because they have 2 eigenvalues, each have 2 eigenvalues equal to 1. Each have a fixed plane, and those 2 planes must at least intersect in a line, which would force the third matrix to also have an eigenvalue 1. Because because of this matrix equation, all 3 matrices must fix that line pointwise, and that would force the third matrix to also have an eigenvalue 1. But if C, D, E are not equal to 1, this is impossible. So it's all, I mean, in this example, it's elementary to solve it, but you can imagine in much more complicated cases, it's not very efficient to argue using this completely elementary way approach. But fortunately, so there has been fascinating advances in this direction. I mean, this is happened in the last century, basically. So this some weak version of this kind of Deligne-Simpson problem has been solved by the work of many people. List some names: Simpson, Crowley, Bowie, Kostov. So, for example, the solution has to do with the quiver representations and Kasmudi root systems. So related to all kinds of well-known pieces of mathematics.
It's solution or reformulation? Because
solution, the weak version, I think Crowley-Bowie proved, so it gives a criterion for the solution to lie not exactly in each given conjugacy class, but in the closure of that conjugacy class.
I think, so I should ask my son, who is an expert, but I think he solved without taking the closure as well. Sash, do you remember?
Probably.
Yeah.
I mean, yeah, there is at least a claim that it's completely solved using these kind of multiplicative pre-projective algebras in the general case where it's not just the closures. But I don't know. I think there's right now, at least as far as I know, there's like a argument in one direction. So it's like not independently of.
Yeah, but even for the you see, you can take like closed conjugacy classes, and there is no difference between like semi-simple,
Yes.
like in your example. But what I'm asking, it's different. Is it a solution or just reformulation? Because I remember that he used some Kac-Moody algebras of which are so wild that they are not affine, they are not hyperbolic.
Okay,
so
yeah, you can call it reformulation, but I guess it's much more. It should admit an algorithm for the computer to decide.
Yeah, so that's a question whether there is an algorithm. So I'm not sure, but anyway, yeah, okay, yeah, I understand. Yeah, okay, good.
Okay. Okay, so our focus will be a variant of this original problem. So this problem, we can call it the tame Deligne-Simpson problem, or regular, because local systems can be identified with connections, integrable connections with regular singularities. Let's just, we always concentrate on the case of Riemann surface. So all connections are integrable. And this is the kind of Riemann-Hilbert correspondence tells us we can think of local systems as all coming from solutions to ODEs, and different ODEs may correspond to the same local system, but if you require these ODEs to have regular singularities, so at most pole of order 1 at the punctures, then it's a one-to-one correspondence.
Yeah, I also kind of have a question. You say Riemann surfaces, but it looks like this problem is non-trivial only for CP1, because otherwise it always has a solution. Because the fundamental group.
Oh yes,
Yeah,
yes,
yeah.
You're right. You're right. Well, I guess one can draw loops, not around punctures, draw actual prescribe a monodromy around actual loops in even on the closed Riemann surface.
Yeah, and so then if genus is bigger than 0, then you can.
Yeah. In any case, we will only talk about P1. Okay, so the irregular version is to drop this regular singularity condition, and we just talk about connections. Okay, so now roughly we can formulate the problem as follows. So given the local isomorphism type of connections at each xi. So I'll be more precise what this means. Does there exist a connection on P1? Well, with the given type. Okay. So we will leave the world of local systems. So this problem doesn't have, at least it doesn't obviously have a formulation in terms of matrices, but it's about connections. And generalize a little bit further is instead of talking about usual connections, we can talk about G connections. Here, G is a complex reductive group, a connected reductive group. Okay, and a G connection locally looks like D plus some one form valued in D. So this is a one form valued in G in the D algebra and up to gauge transformation. So
gauge, so because I have a question, your gauge, it can be formal or it can be analytic, does it matter?
So when we talk about the local isomorphism type, we are talking about the formal type, up to formal gauge transformation.
Okay.
And the existence is about global algebraic G connections. So that's yeah, so that it makes sense to talk about regular singularities. Algebraic. Okay, so our focus will be P1 with 2 points removed. And at infinity, we will prescribe some irregular type, isomorphism type. So this will be a connection on the formal punctured disk. We see double bracket tau. So here I use tau to be T inverse as the local coordinate at infinity. So I'll be more precise about what it looks like locally, because that's important for the formulation of the theorem. At 0, we require it to have regular singularities, and we will prescribe the residue to be, now it's some adjoint orbit. And so the locally at t equals 0, this looks like d plus some a0 over t plus some higher term, holomorphic terms, t, and I require a0 to be in the prescribed adjoint orbit in the algebra. So this is a regular at t equals 0. Yeah, so roughly speaking, our result will be a criterion. So given this adjoint orbit and the irregular isomorphism type at infinity, we will give a purely algebraic or even combinatorial criterion when there exists a G connection on P1 with these singularities. Okay. But to formulate it, I need to talk more about irregular.
So, sorry, may I ask you a stupid question because I forgot. If I have irregular connection on the formal disk, can I always construct algebraic connection on P1 with two singularities? One is irregular and the other one is regular.
That's
in
right.
0. So then you just fix the conjugacy class of the residue of this extension.
Yeah, that's a very good point. Yeah, maybe I think it's worth making a remark here. So this is kind of a Katz extension. So given the connection near infinity, at the formal connection at near infinity, there actually is a canonical way to extend it to a connection, given even a GG connection or G connection on P1 minus 0 infinity, such that it has at most, at worst, regular singularity at 0. So you can always extend it in some way, even in a canonical way, not in a unique way, but Katz's singled out canonical way of doing it. Here, we want to be more constrained so that the residue lies in a specific adjoint orbit. Okay. So let me recall something about local stories of irregular singularities. Let's first, just for the usual connections. Okay, so the usual, or G equals GLM. So the simplest kind of irregular singularity is you just add higher poles, right? So you can have an over t to the n. So I will use tau as the coordinate at infinity. So let's just take the polar part, so a1 over tau and d tau over tau. So writing this way, I only keep the irregular parts. So this already has a simple pole, and here always have pole of altogether have order of pole at least 2. And then the rest are regular singularities. So this is the simplest kind of connections to write down. But well, you can even restrict it to the case where all the AIs are diagonal matrices. So basically, this polar part, irregular polar part, looks like a direct sum of one-dimensional connections, because all these are diagonal matrices. And this is not far away from a general form of an irregular connection. In fact, general, so up to formal gauge transformation, every irregular connection looks like this if you're willing to pass to a covering of the disk. So it looks like this after a base change. So after pull back to the disk, maybe the mth cover of the disk. Because the original disk is has coordinate tau. You introduce mth root of tau for some m, and then you pull back your connection. Then for a suitable choice of m, you can then diagonalize all the terms simultaneously under gauge transformation of this covering disk. So we can write this. So after introduce this root of tau, we can write it as following. So a of d over n, tau to the d over n. So now its leading term will be some fraction power of tau, because it's an integral power of tau to the 1 over n, and some lower terms. Okay, so tau over tau, or you can use the variable 1 over n. There's not much difference in the regular terms. So this connection will look like this up to gauge, such that all the ai over n are diagonal. And so this leading term is called a slope. And well, sometimes it's a little ambiguous because if you have a leading term, if it looks like this, 1 and a 0, then it looks like it has a, if you think of this as a direct sum of two one-dimensional connections, then the first one corresponding to the one here, it's reasonable to call it has slope d over n, but the other one, it has a leading coefficient 0, so its slope should be smaller. So in fact, to each formal connection, we can assign not just one slope, but a collection of slopes. But now we will restrict to what we call isoclinic connections, isoclinic irregular type. This means the leading term is regular semi-simple as the algebra element in GLN. So it's not quite saying that you're not allowed to have 0 in the diagonal. It's just saying all the diagonal entries are distinct. Diagonal with distinct entries. So this kind of connection we call isoclinic, and its slope is called, this d over n is called its slope. And this kind of connection, this notion generalizes to G. We just say the same words, but what I described as this local structure theory, this is the Velt-Turretin theorem about local structure of a connection up to formal gauge. So it's saying passing to a ramified cover of the disk, you can write your connection as a direct sum of one-dimensional connections. And then we call those whose leading term is regular semi-simple isoclinic. And this notion generalizes to arbitrary G. Okay, so one thing, so one remark is that this slope is not arbitrary. So which rational numbers can be the slope of an isoclinic irregular type? So possible slopes of isoclinic. So these are highly constrained on the denominator of such slopes are highly constrained. So we write the slope mu as d over m in lowest terms. Then this n, so in the case of GLN, usual rank n connections, n must be either a divisor of n or a divisor of n minus 1. Okay, so this, so this is a highly constrained, and in general, what happens is that the condition on this n is that n must be the order of a regular element in the while group of G. So, I mean, the regular is used in several different contexts here. This notion of regular element is due to Springer. And an element W in W is called regular if it has an eigenvector. So if look at the action of W on the carton, this action has an eigenvalue, has an eigenvector that is regular, semi-simple. So it has an eigenvector not lying on any walls. Not killed by any root. So now we come back to this example, GLN. Why should n be either a divisor of n or a divisor of n minus 1? This is because, just to check against this general principle, we're talking about orders of regular elements in Sn. So in Sn, regular elements there are two kinds. One is that they are permutations of cycles of equal length. Okay, so in other words, they are just take a cyclic permutation and raise it to some power. All cycles have same length, or almost all cycles have the equal length, except for a singleton. So I'm allowed to have this. This in S7 is also regular. So only these two kinds of permutations have eigenvectors that are not lying on any wall, so they have distinct coordinates. And their orders, it's clear from this description, the order of such elements are either a divisor of n or a divisor of n minus 1. So this is what's happening for GLN, or if we restrict to isoclinic connections, the slope is has denominator that's either dividing n or dividing n minus 1. And in all other Lie types, these regular numbers are completely determined by Springer. So for example, for E8, there are 12 possibilities. Okay, so the largest one is always the Coxeter number. And usually 2 is also one of them. It's the smallest, well, 2 and 1, of course. 1 is identity element, is a regular element. 2 is often a regular order of some regular element. In this case, the while group, the longest element in while group acts on the carton by -1. That element is regular. So 2 is the order of that. And there are things in between. I mean, divisors of 30, they're all regular, or all possible m's, but a few others. Okay, so this is just some numerics about the slope. And now we can, let's see if I have all the ingredients. Yeah, so our goal is to solve the following Deligne-Simpson problem. So we are given an isoclinic irregular type at infinity. So meaning it's some Laurent tail. So some slope mu. d plus this d tau over tau. This irregular type only refers to the polar, like irregular parts. It's just the Laurent tail. So the regular part is not prescribed. Yeah, so this A E over N inside the G is a regular semi-simple. And we are given an adjoint orbit. This is supposed to be the residue at 0 of the connection. And we want to answer a yes or no question. So does there exist a G connection of P1? It's 2 points with prescribed local behavior. As above.
So may I ask you about this condition at infinity? Like if, for example, it was a regular singular point, then you fix the whole coadjoint orbit, and now you fixed just the tail and not the classic of, I mean, if, for example, d over n was equal to 1, then you should fix a conjugacy class of this a d over n, and now you kind of fix it itself. So it's a bit confusing.
Fix.
Sorry, yeah, like imagine that you just hypothetically that you have two regular points, yeah?
Yes, yes.
Then probably you would say that you fix a coadjoint orbit at 0, that's fine, but another one, it should be also coadjoint orbit, because, and now you are saying that you fix just the tail, the matrix itself, not the orbit of this matrix, but you fix it itself.
Well, what I wanted to say here is it's gauge equivalent to this. I'm not.
You fix the gauge equivalence. Okay. You fix a gauge equivalent class. Okay, good, yes. Good. Yeah, all right.
Okay, so it turns out this yes or no question only depends on the kind of numerical data here. The answer only depends on the numbers, these two numbers. One is the slope, and not completely on numbers. One, just the data at infinity, all I'm going to use is the number here. It actually, this leading term or the other terms, they don't affect the answer. And at infinity, of course, I do need to just take this adjoint orbit. So the answer will be formulated just using these two pieces of data. Okay, now in order to give the answer, let me recall this double affine Hecke algebra, and more precisely, I'm using a degenerate version of the rational Cherednik algebra, which is some kind of double affine Hecke algebra. The starting point is the Weil group of G, and it's an algebra that's roughly of the size polynomial function in the size of the twice of the so it's the double affine. There's nu will be a parameter which eventually will be the same as slope. So as a vector space, this is this algebra is polynomial functions on Cartan, polynomial functions on dual cartan and the group ring of the Weil group. And there's the usual, the algebra structure is, or there are three kind of rules how you commute elements from each piece. Right, so the W will act on H and H dual. So these two pieces just commute in the usual way. It's a semi-direct product. The most interesting commutation relation is when you take an element from here. So you take an element, take a maybe call it. Okay, so this is the symmetric power of H. So I take an element X from H. This is symmetric algebra of H dual. Take an element of C. So when I commute X and C, they're pairing with some interesting correction term. And this number will show up in this correction term. The correction is you sum over all roots of G. So, use these kind of pair. This is, well, if I just write this number, this would just be killing form. But this is the reflection corresponding to alpha. So this element lies in the group ring of W. Okay, so if it's first time you see it, it probably doesn't make all much sense, but it is it has a double affine flavor because it has two polynomial rings in addition to the finite Weil group. If you sort of take nu to be 0, you just ignore this part, then this becomes the Weil algebra on the symplectic space H plus H dual, and it's the semi-direct with W. Okay, but this algebra has a very rich representation theory, and in many ways it behaves like the universal enveloping algebra of the usual semi-simple Lie algebra. So this decomposition is reminiscent of the triangular decomposition of the Lie algebra. So this looks like a cartan. This is an upper triangular, lower triangular. So you can talk about category O for this modules over this algebra, Verma modules, and so let me ignore all those details.
So is the summation over all positive roots or just all roots?
All roots, all roots.
All
but
roots.
you can rewrite it just using positive roots. Then you don't need to divide by 2.
Okay, yeah, thanks.
Yeah, so it has particular representation, irreducible representation, irreducible module. That is a quotient of the Verma module. So triv here, meaning you put the trivial representation on the Weil group, and then you also take the augmentation modules, it's just C here, and then just induce up from this part. That's the Verma. And then that has a unique simple quotient, which we denote by L nu triv. So if this nu has denominator n, which is the order of a regular element, a regular elliptic element of W. Okay, so before the notion of a regular element in W showed up, now I impose slightly more restriction. I want it to be elliptic. Elliptic just meaning no eigenvalue 1 on the reflection representation. Okay, so it's a smaller class of elements. And if M happens to be the order of one of such, then this L nu trig is a finite dimension. This is actually if and only if. Okay. And there has been a lot of work trying to understand this representation. For example, what in particular, since the rational Cherednik algebra contains the group ring of W, it is any representation of it is also a representation of W, and we can try to decompose it into irreducibles of W. See, each representation appears with which multiplicity.
Zhiwei, may I ask a kind of very general question, because I'm ignorant in that? Is there a localization theory for a rational Cherednik where G mod B is replaced by something else, like a fine Grassmannian or something?
Yeah, that's a very interesting question. I don't immediately, so there are geometric realizations of representations of this rational Cherednik algebra. Which is more in the spirit of Springer representations. This kind of Weil group part, Weil group representation realized on the homology of Springer fibers, and the modules of this guy are realized on the homology of affine Springer fibers, which actually is relevant to this talk. But I can't see why that is analogous to the kind of Bernstein localization. Yeah, that's.
Yeah, I asked because you mentioned that there is an analog of the category O,
yeah.
and then it's obvious that. Yeah.
Oh, I mean, okay, so maybe along those lines, this is, I think, abstractly, it's isomorphic to differential operators on, at least over some generic part, it is the same as differential operator. It's a W equivariant differential operators on H. So, you know, there's this KZ functor that maybe that's closer to the Bennington-Bernstein localization. You have a module here, you can localize it to a D module on some open part of H. KZ functor. But that's sort of at the opposite end of the spectrum from what we are considering today, because these finite dimensional representations will be killed by that kind of localization. Okay, so the answer, the main result is some simplified version can be formulated as follows. So this is let's again recall our given data is some irregular type, isoclinic irregular type. With this slope d over m, but now we know that this m has to be a regular order of some regular element in the Weil group, but now I require it to be the order of a regular elliptic element. This is only slightly more restrictive than allowing all regular elements, and you know, the actual theorem we can drop this condition, but it's easiest to formulate it with the assumption that it's elliptic. And at the other singular point, we have to add one orbit, but for simplicity, let's assume it's a nilpotent orbit. Okay. Then the Deligne-Simpson problem has a solution. Given the local data, it has a solution if and only if we look at this mu triv. This is a representation of a complicated ring, but in particular, it is a Weyl group representation. And the condition is that it contains the Springer representation corresponding to O. Corresponding to this nilpotent orbit and the trivial local system on it. Okay. So I don't know, you may call this a reformulation, but people know a lot about how this representation decomposes as a Weyl group representation. And there are tables you can look for exceptional types. And Emily Norton is an expert on this. And based on those results, one can effectively decide when the Deligne-Simpson problem has a positive solution. So that's a general result that, I formulated it under some more simplifying assumptions, but the general result takes the same form. I also want to mention when G is classical, we have a more explicit solution in the sense that it doesn't require understanding representations of rational Cherednik algebra. We just give which nilpotent orbits are allowed. So given the slope B over M, there's an explicit determination, explicit nilpotent orbit O nu of G, such that the Deligne-Simpson problem for mu and O has a solution if and only if this O, well, if O is nilpotent, I would just say this O closure. So O is bigger than this particular nilpotent orbit that's determined by the slope. Contains it in a closure. And if O is not nilpotent, the general adjoint orbit, there's still a way of saying the sentence. So you just, you take the orbit, scale it. So this is it's not a single orbit anymore. You take its closure, then it will meet nilpotent cone. And you just require that to contain the given nilpotent orbit, which only depends on the slope. So now I need to tell you what is the smallest allowed nilpotent orbit, so that given the slope, what is the smallest nilpotent orbit so that the Deligne-Simpson problem has a solution. So O nu is first, it's easier to formulate it for GLN. And for GLN, this is obtained earlier and using different methods by several authors, Parney, maybe say Mathern, one, and say Daniel Sage. So that was it was really their work that motivated our work here. So they work with GLN. They explicitly determined those, they solved the Deligne-Simpson problem, the same Deligne-Simpson problem in the case of GLN by different method. And so what is the answer? So, well, the smallest allowable nilpotent orbit is if you just take an example, slope is d over n. Okay, now d does not have to be prime to n. Then this O nu is just the most balanced. Well, I should say smallest nilpotent orbit with at the most d Jordan blocks. At most d Jordan blocks. So smallest meaning you need to distribute the size of the Jordan block as balanced as possible, as evenly as possible. So the longest Jordan block and the shortest Jordan block size differ by at most 1. And if nu is d over n minus 1, it's the same. It's except that you're just partitioning n minus 1 instead of it. It's similar. And for other classical groups, the answer is also similar but more complicated. So in terms of it's always given. So that's our calculation. So answer is given in similar terms in terms of Jordan blocks of this minimal allowable orbit. But I mean, we have a table in the paper. One sort of easy consequence of the theorem is that if the slope is at least 1, then there's then all adjoint orbit is okay. So there's no constraint on the residue at 0, as long as the slope is at least 1. Okay, and I think this is also just easy to see directly. One can probably just write down a connection. I didn't think carefully at this point. So maybe just last minute,
yeah, you can go over the time because anyway, you will have to because I have questions. Yeah.
Okay.
When you finish. Yeah. Okay. Proof idea. Yeah. That.
Yeah. Maybe because you have questions, then maybe I should.
No. This was one of my questions because
okay.
The answer is nice, but what's the idea?
Right. I'm sort of trying to. I should try to demystify how the Deligne-Simpson problem is eventually related to these objects, seemingly unrelated. So proof idea is to consider the moduli space of connections with we can add these decorations like mu and O, so, with prescribed local conditions that there's a moduli space of such, and it has a degeneration into Higgs field, Higgs moduli space. Where the connections degenerate to, maybe I shouldn't put O here.
You mean like this lambda connections, like
lambda connections?
Yeah. Okay.
Lambda goes to 0. I want to prescribe the irregular, certainly the slope and the irregular type. I may or may not it's actually it doesn't make much difference. You prescribe all these A, V over M, or you just let them vary also. It's sort of, the moduli space is smooth in that direction. It doesn't really matter. So this geometry of this moduli space was studied in my paper with Bezrukavnikov, Alvarez, so Pablo Alvarez, Boixeda, Michael McBreen, myself. In the earlier paper, we systematically study such moduli spaces that sort of arising from the same data, mu, slope. And we explore various aspects of non-abelian Hodge correspondence. So this is a kind of variant of Simpson's picture, but with some irregular singularities at infinity. And what we are looking for is a point here. And given sufficiently nice family, the existence of this point is equivalent to the existence of certain limit point under the flow so there's a GM action on this whole family, right? On this whole family.
Sorry, I'm confused. Because when you have nu and you do not have this orbit O, it's one story. If you do have an orbit O, you cannot fix, or can,
I'm not fixing O. So
you're not fixing O. So then
yeah.
You are asking not about the point in M deram nu, you are interested in the end in the point of M deram nu, comma O. You should.
Yeah, so
yes.
I'm interested in point, with the O condition, but so the claim is that a point here with this both nu and O condition will give rise to something here that's nu, of course, but then it will be I can't say that the limit still has the residue O, but it's certainly in the closure of O.
Mm-hmm.
And if O is not nilpotent, it's in the closure of the scaling of O.
Scaling.
So this is a kind of a way, canonical way, starting with an arbitrary adjoint orbit, you can get a nilpotent orbit.
Okay, that's why nilpotency is important, because otherwise your eigenvalue get changed when lambda goes to 0.
Yeah, exactly.
Okay.
So we analyze the geometry of this family, and the conclusion is that the Deligne-Simpson problem for nu and O is equivalent to a point in the Higgs moduli space with the residue with residue which is nilpotent orbit in the closure of GMO. I mean, there's some argument that needs to be done here, because if my residue is really small, how can I make sure originally it started life within some bigger orbit? So there's some kind of flatness argument that needs to be done here. But anyway, we reformulate the question about existence of certain points in the Higgs moduli space. And the Higgs moduli space, as usual, has a Fitchian fibration. So it's Fitchian base, Fitchian map. And the central fiber turns out to be the affine Springer fiber. So this was also proved in this joint paper of 4 authors. And we proved, for example, this Hitchin map, that this whole thing is a completely integrable system. Realizing this affine Springer fiber, a particular affine Springer fiber, as a Lagrangian inside some symplectic manifold, which is, and at the same time, there's a contraction of this symplectic manifold to the Lagrangian. So this is a affine Springer fiber. Let's call it this is a Grassmannian version of affine Springer fiber. It's called gamma. This gamma is essentially this leading term. So it's E over M tau T over M. This is exactly the same data as this. Okay, so this is now some subvariety in affine Grassmannian, and this condition about residue in the closure of something is the following. So Grassmannian gamma is the set of points G inside cosets in G double bracket T, such that adjoint G inverse of gamma lies in G of O, around power series T. Now this, if you have such a point, you have an integral matrix, and then you can mod T. Now the reduction is necessarily nilpotent because gamma is topologically nilpotent. So here, gamma, this guy. Written in terms of T, not tau, it will be topologically nilpotent. So just that setting T to be 0, you will get a well-defined nilpotent class, nilpotent orbit. And so the question is just whether the image of this map intersects this orbit closure. Okay, so we've further reformulated the problem as a problem about affine Springer fiber, whether this is called a reduction type, whether it has a point whose reduction type is smaller than some nilpotent orbit. And this is the kind of problem that I studied in my other paper, which I solved the conjecture of Kashtan and Lustig about, in their original affine Springer fiber paper. But in any case, so this at this point, the two theorems then use different techniques to answer this question. One uses my work with the Oblomkov that says that in the cohomology of this affine Springer fiber, there's the flag version, there's an action of the rational Cherednik algebra. And this reduction type, which nilpotent orbits appear, can be detected by looking at which Weyl-group representations show up in that module for that double affine. So that leads to theorem 1. Theorem 2 relies on a more explicit study of these varieties in the classical types. And so that's doesn't use double affine Hecke algebra, but relies on some result in my other paper. Okay, I'll stop here.
Thank you very much. Yeah, it looks like kind of your proof is much more deep than the original problem itself. Yeah.
Well,
yeah, but
okay.
yeah. I mean, I have several questions. So one is the following. If, for example, okay, imagine that I'm in GLN, G equal GLN, so there are some other works which you mentioned previously and some of them which you did not mention. But there are two types of Deligne-Simpson problem. There is a multiplicative, which you've been talking about for connections, and there is an additive, which I believe is for Higgs bundles. Now you somehow reduce the multiplicative problem to the additive one, but with a different local behavior of Higgs fields, if I can say it. So I'm just curious whether possible to do it, let's for GLN, but for more general setup, like you have only 2 points, 2 mark points. If there are many points, yeah. So what?
Yeah, I'm sort of this proof sort of heavily relied on the existence of GM action, which is so sort of if you have 3 points, then there's no chance. GM action. I mean, I'm not saying it's impossible, but it would rely on more serious study of Simpson correspondence with irregular singularities. But here it's somehow we don't really need to know much about these moduli spaces. We don't need Simpson correspondence. We just need to degenerate one to the other.
Yeah, I don't know. I mean, I remember I spoke to Roma Bezrukavnikov about that paper, and this Lagrangian, I mean, it's like complex Lagrangian sitting in something symplectic. It's like Sladovius, I mean, some slide. Yeah. I mean, in symplectic topology, in the C-infinity setting, they have this story in mirror symmetry that you have a symplectic manifold, you want to find a Lagrangian skeleton which is singular. In that story, it's real, not algebraic or complex, and such that the whatever global category you consider for your symplectic manifold, it's equivalent essentially to the category of modules associated with this Lagrangian skeleton. So, which means that there might be, I don't know, in this global story, either a possibility to have this analog of the Lagrangian skeleton, which is no longer comes from the local theory, from the fine Grassmannian, but in some, I don't know, global sense. Probably you can say it better because you have papers on global Springer's theory. Yeah, I mean, I really want to have several points. It's basically, yeah, I'm just trying to kind of to speculate what could it be. Because, for example, for irregular Deligne-Simpson, you know, there were papers by this Hiroi, Yamakawa, some Japanese people. They considered existence of a connection on a trivial bundle, yeah, sort of an open part, but for many points, and they have some criterion which mimics this Crowley-Bowie stuff, Kac-Moody algebra, this kind of things. Yeah, but anyway, it's for several points on CP1, and just asking whether it's possible. Yeah, I understand that you need, for some reason, you need GM action, but kind of what is GM action? Is it just a way to prove things, or it's really absolutely necessary, or you need this sort of a Lagrangian a skeleton and some replacement of the Sladovius slice or something like that? So that's kind of because you have a very powerful technique. It's so kind of, it's like
Okay,
you use it. Yeah.
Yeah, I mean, I should say I'm not, you know, it was not my original motivation to solve the Deligne-Simpson problem. It's
Yeah, I can
really,
guess. Yeah.
I know the geometry of these objects, and this is the application. So I'm sort of
Yeah,
holding a
I
key and looking for which
Yeah,
door
I
it
see.
can
And
open.
those people, like, which whatever, 3 or 4 people, including Sage, which you mentioned in the end, did
Yeah.
they solve it just for 2 points?
It's also for 2 points. Yeah,
Also 2 points
it's the same set.
by different methods. Okay, let me ask another question. In this Deligne-Simpson problem, people also asked about moduli space of solutions. If you have one solution, you maybe want to have the whole moduli space, and the question is how to describe it. For example, Alex, my son, he did it in this Crowley-Bowie framework, I believe, but there is a description that somehow something like normal crossing or something. Maybe he can say it better than me. But there is a kind of theorem which tells you how this moduli space of solutions look like. So in your case,
In my case, well, it is this moduli space with the O added.
yeah, but
The geometry, I only know its limit. I really don't know. Well,
probably it's
homology I can
homeomorphic. Is it homeomorphic to its limit?
hopefully. I don't. Well, my co-authors, in the 6th author paper, other people know better about the status of Simpson. Simpson correspondence in irregular connections. But I don't know the literature so well.
That's fine. That's fine. No. I mean, just so you do have some description of the moduli space, maybe up to homeomorphism, so which means that you don't know what the algebraic structure.
Right.
Well, but in terms of the limit. Okay. Good.
One kind of I'm curious about one question. I don't know if people have thoughts. So if we compare to the Simpsons picture, so there's this GM action taking a connection to some Higgs field, a nilpotent Higgs field, and the GM fixed points in that case correspond to variations Hodge structures.
Yeah, from
So
complex relations.
Here we have a similar picture. We have GM action and taking fixed points. So these will give some subvarieties in the affine Springer fiber. Those are smooth projective subvarieties. Can be described explicitly. There are complete intersections. So I wonder about any Hodge theoretic meaning of those fixed points.
Mm-hmm.
It's a vague question, but
Yeah. Yes, so it's indeed it's interesting. Yeah. All right. And okay, yeah. And since you need this GM action, so it's basically the most general problem which you can state and solve. Yeah, okay. Indeed, it's rather application of your previous paper with many co-authors, and to Deligne-Simpson. Yeah, okay. Okay, so which means that no other curves with 2 points and no P1 with many points. Okay. Yeah, good. Good. All right. Let me see. Yeah. And no kind of translation of what you've done to the language of quivers, because probably Hiroi and other people, they do have some answer in this
Well,
case.
I would imagine it's a type A story.
Yeah, in their case it's type A, so for you it's GLN, but can this, whatever they construct, probably some sort of quiver varieties. And I don't know, you also have some symplectic manifolds. Yeah, so I don't know, maybe you or your co-author, maybe you thought about the relation to this quiver language.
I haven't, yeah, I don't.
Yeah.
I mean, when in the tame case, when the underlying bundle is trivial, I can sort of see why it's related to quivers, but in the irregular case,
Yeah, in the regular, yeah, this Hiroi, Yamakawa, Sasha, is it true? They considered this some kind of a quiver, but in the associated with irregular data, and after that they rather mimic in some clever sense what Crowley-Bowie did before. But the relation of whatever quivers they construct to the geometry which you consider, it's not clear. Yeah.
Okay.
Yeah, it's a question. It's a question. Because yeah, I know. I mean, my son told me more about those quivers story, but I cannot translate immediately because it's all finite dimensional. No, yeah.
Can you get the names of the Japanese authors?
No, you have it. It's Hiroi and Yamakawa. You have this reference.
In our paper, yes.
It's irregular. Yeah, it's in your paper, but it's a different approach. And since, as I said, I think about Crowley-Bowie stuff as a reformulation of, okay, now you give some reformulation of Deligne-Simpson problem in your case, and they give another reformulation in their language. In your case, you said that it's not just reformulation, you can solve it completely, which means you can list them based on the representation theory of W, whatever. But I'm not sure that they can say the same thing, but at least the question is how to match two languages, the one which you used and the language of quivers, which they did. The quivers are rather not difficult to understand, but they it's sort of, well, my picture, it's not, unfortunately, it's not algebra geometric. I can tell you how these local quivers appear from the local problem, but I need to go from M Deram to M Betty. I need to use a Riemann-Hilbert. Although no, they do describe quivers also directly from the HLT normal form, but maybe it's not maybe they consider unramified, they do not go to the finite cover of the formal disk. They consider the case when your pole is integer, d over m is integer, probably. That's one thing, but otherwise, but I have very, very simple description of their local quiver. When you, but you should use this stock structures, what appears in on the beta side. Okay, so maybe I can, if you are interested, I can tell you. If you are not, then I will not tell you. Yeah, all right. Okay. Yeah, maybe last thing which I would like to ask you is to email me your notes.
Okay. Yeah, sure.
Yeah, good. And then are there any other questions?
Yes, so let me try to understand that. And the original question was just taking conjugacy classes in the reductive group over the C rational points.
Yes.
And so now when we do this for the curve with the function algebra, so you are taking the conjugacy classes, some sort of taking conjugacy classes inside of the reductive group with the rational points in the function algebra. Am I correct?
In some sense, only the tail, Laurent tails.
So mainly you focus on these singular parts. And my second question probably, already asked about the quiver approach. The best way to think of a quiver is that you have a reductive group if you have a Levy factor. And for the Levy factor, suppose you have a solution with how does that, similar to the neopotent orbits when you do the induction, how to go from, say you have a solution on the larger reductive group, but on which Levy subfactors you might have a solution or not.
If you have a solution in G, you ask whether the solution can actually sit inside some
Levy factors.
Well, okay. I mean, this criterion works. You can just apply the criterion for the Levy subgroup. I don't know.
Yeah, because you have the criteria with this the TM or action or on the orbit and the closure. So the question is that because on the Levy factor, some of the orbit closures could be much smaller. Yeah, that's what I was while listening Jan's question about the quiver approach. That's my way of understanding the type A. The quiver is just going from Levy inside of a reductive group. If I have many blocks of Levy factors, each factor gives me a vertex of a quiver.
Yeah, the way there is a way to construct this. There are different ways to describe this quiver in the irregular case. For example, there was a paper by Bolch, who probably the first one who connected quivers with irregular connections on P1. Yeah, but there are others. So it's not, the question is rather whatever quivers are, what's the relation of that story to the one which Zhiwei explained to us. Because you know it's this you know this the generation story is so nice that it's I mean it would be nice if it had the same range of applicability than this quiver story, but for some reason probably it requires more techniques. So yeah.
Okay, that's all what I will ask you. Well, thank you, Zhiwei. It's a very, very very interesting
it's
and a
very
matter
nice.
way to understand material. First, I look at the paper, didn't quite understand.
Okay.
Yes, but you still have time to understand it better. All right. So if this is it, are there any other questions I should formally ask? That. Okay, if there are no more questions, so I remind you about sending me notes, and thank you
I'll
again.
do it tonight. Yeah.
Thank you very much.
Thank you for the invitation. It was a
Thank you.
pleasure. Yeah.
And this is it for today.